So welcome to the ninth colloquium lecture in this session. And today's speaker, Yuval Grossman, is quite well known. So it's a pleasure to have him as a colloquium speaker. And he didn't need much introduction. As you can see from all over the places, people have come for this colloquium. Just to listen him, but for the sake of our young audience, I would like to say a few things about him. That he graduated from Weizmann Institute of Science in 1996, and from 1996 to 2000, he was associated with Stanford Linear Accelerator Center, Stanford University, and he remained there until 2000. And 2000 he joined Technion as an assistant professor, and again he remained there until 2007. And in 2007 he joined Cornell University, and right now he is there as a professor. His research interests lie in various areas, starting from clever physics, neutrino physics, and collider phenomenology. And today he will be talking on very interesting topic, like three questions, one answer. Neutrino as the key to understand the universe as we know it. And before I hand over the forum to him, I would also like to thank our colleague Sumitro for initiating this invitation, because once I discussed with him that we need some particle physicist for this colloquium, he told me let me try to Yuval, and Yuval agreed over that. So without doing any further delay, I hand over the forum to Yuval and invite him to deliver today's physics colloquium.
Okay, thank you very much, guys. Well, I forgot my my clock. Okay, you should remind me when times go on. Anyway, so I'm happy to be here, kind of in India. It's been so long since last I visited India, so I really hope that soon we'll be able to come back and do it. So today what I want to talk about is the title is the 3 questions, 1 answers. And what I want to talk about today, I want to tell you 3 different kind of open questions in physics, in high energy physics, that seems unrelated. And I'm going to describe to you those questions. And there's some possible answer to those 3 questions. And one possible answer actually turned out to be the same. And maybe that's an indication that something deeper going on. So what are those 3 open questions in physics, okay? So the first one is how neutrino acquires their tiny masses. So we know by now that neutrino actually do have some mass, and it's much smaller than the mass of the other particles around us, except the massless particles, of course. And the question is, what is really the mechanism that gets these neutrino masses? And a different question is why there is only matter in the universe. So we expect some general thing that there should be actually, then matter and antimatter should exist in the same amount. And somehow we have a universe that's made out of matter only. And we're not sure we really understand the answer. And the third question is why the electron and the proton have exactly the same charge, absolute magnitude, of course. So if you think about it and you look at the masses of the particles, each particle, the masses are all over the place. Like the electron and the proton mass are very different, the neutron mass, everything. And then suddenly the electron and the proton has exactly the same mass. I mean, to all precision that people try to look, the electron and the proton has exactly the same mass. Has the same charge. Of course, the mass is very different. So why is it? Okay? And as I'm going to argue is that it's plausible that there's actually one solution, one underlying deep physics that actually give answer to those 3 seemingly unrelated questions. So this is my outline. I'm going to start with a short introduction to high energy physics. Kind of tell you why it's possible that there's one answer that explains everything. Okay, so let's start. Oh, let me also say that if you have any question in the middle, please feel free to interrupt. I love to have some discussion, particularly now that I don't see you and I just talk only to the computer. will be great to have some interruption. And also let me say that this colloquium is aimed for people outside particle physics. So all my friends here in particle physics, of course, you know, this should be all known to you. So let me start with the introduction for high energy physics. And that's the way I actually explain what high energy physics. It's a very simple question. And I'm so proud of this little equation. It's the shorter equation one can write, L equal question mark. So that's what we are really trying to do in high energy physics, is to find a fundamental Lagrangian of nature, okay? And the question is how we even actually get into this kind of, how to address this question, how to find the Lagrangian of nature. So the tools that we are doing is what we call, we build Lagrangian. In a way, it's a little bit old-fashioned name. I think that in those days we could say we are a designer. We design a Lagrangian. But we still use this old-fashioned name, built Lagrangian. So how do we build Lagrangian? What does it mean to build a Lagrangian? We want some Lagrangian that presumably eventually going to describe nature, okay? So we do it basically just like we do classical mechanics. And though, you know, you remember in your undergrad days when you learn analytical mechanics the first time, you say, how do you know what is the Lagrangian? You say, well, you just tell me what are your degrees of freedom. We call them generalized coordinate. And in high energy physics, our fundamental building blocks are the fields. They are not the particles. Like in classical mechanics, we have particles. In high energy physics, we have fields. And then you impose some symmetries, and you tell you how those fields transform. For example, when you do classical mechanics, you say, my degrees of freedom is the position of the particle. Let's call it x. And I say this x is a vector under rotation in three-dimensional space, okay? So we do the same in high energy physics. We say our fundamental degrees of freedom, which are the fields, they can be a scalar or a vector or some tensor transform under some space. The space is not real space, it's some other space. But it's the same idea, okay? And then just like in classical mechanics, what we do, we write the most general Lagrangian that obey those symmetry, right? So in classical mechanics, you say, oh, I have time translation, X translation and all this, and I write the Lagrangian for a free particle, and I find that it must be some number times v squared, okay? That's great. It's just some, you just write something that is invariant under all the symmetries. We do the same in quantum field theory. I mean, it's basically a very straightforward generalization of classical mechanics. And then we do what every physicist really loves to do, and we truncate our Lagrangian, okay? And that's the joke I'm telling all my students all the time is if you go on the street and you meet a function, what you do to the function. So of course, you know, as a physicist, when you meet a function, you expand the function and truncate it, okay? And that's a good thing to do a function, okay? So you always, when you have something in physics that you don't know how to solve exactly, you expand and truncate. And the question is where you truncate has to do with how precise you want to go in your experiment, or how precise you're able to go with your experiment. And in high energy physics, we usually truncate at dimension 4. So we have some expansion in some parameter, you know, just like we have a pendulum that we expand in theta, and if you truncate after second order, you get the harmonic oscillator in theta. If you go to fourth order, you get something else. The same in high energy physics. We take our thing, write it, and truncate it. Okay, that's great. And then we have our most amazing theory that come under this almost kind of mundane name of the standard model. And it's an amazing thing. It's explained almost everything we see in nature. It's a huge statement. And while I'm not really going to get into the details of this theory, I put it in one transparency just to show you how compact we can make actually our best description of nature. And it's so compact that there's still room. You see there's still room here, there's still room here. And actually this statement is not part of the model. This is the model, that's it, okay? So our description of nature came down to a very compact, very nice model that applied the principle that I was just telling you before, okay? You tell me what the symmetry, it's SU2 cross SU2 cross U1, and I tell you what are the fundamental fields. I have a quark field, and I have lepton fields, and I have one Higgs field, and the Higgs field correspond to spontaneous symmetry breaking that give us the fact that the weak interaction is very short range, and the W and the Z are massive, okay? So basically that's it. I'm not going to describe to you the standard model. All I wanted to kind of deliver the point is that we have this really simple, based on very simple axiom, just like classical mechanics. We just use this simple axiom. We have some input, we write the most general Lagrangian, and boom, it's explain everything, basically everything, okay? And in order to go on, I want to discuss the aspect of symmetry. Symmetries are clearly an amazing and important part in physics. And I want to distinguish between two kinds of symmetries. The symmetries that we call input are the symmetries that we impose. For example, when we write a Lagrangian in classical mechanics, we impose rotation invariant. We say we impose the fact that our Lagrangian have to be invariant under rotation. Okay, or when we do relativity, we impose Lorentz symmetry. We require that our theory is invariant under the symmetry. However, there's a different kind of symmetries that I call them symmetries that are output. Okay, these symmetries are due to truncation, and we call those symmetry accidental symmetries. Okay, they are not something that we put into the Lagrangian. They are there only because I take my Lagrangian and I truncate it in some order. And probably the most famous example of an accidental symmetry is the famous fact that the period of a pendulum doesn't depend on the amplitude, okay? So it's a well-known fact that the period of the pendulum doesn't depend on the amplitude, but of course this is only an approximation, okay? It's an approximation. Why? Because we take the pendulum and truncate it at the harmonic order. And when we truncate it at the harmonic order, suddenly the Lagrangian gain an extra symmetry. What is the extra symmetry that we gain when we truncate the pendulum at second order? The extra symmetry is what we call dilation. Is the fact that x go to lambda x become a symmetry when we have a simple harmonic oscillator. But I want to emphasize that this dilation symmetry, x go to lambda x of the simple harmonic oscillator, is an accidental symmetry. It's there only because we truncate the pendulum at second order. If we keep the theta to the fourth term, then suddenly we don't have this symmetry. And as we know, when we keep the theta to the fourth term, actually the period does depend on the amplitude, okay? So it's important to kind of make the distinction between those two kinds of symmetries. So what are the accidental symmetries of the standard model? So in the standard model, the accidental symmetries are baryon and lepton number are accidental symmetry. And we usually say why the proton is stable. And actually, I just got this question yesterday in my class when I was teaching here at Cornell. And the standard answer that we all say, oh, there's some conserved quantum number that we call baryon number and lepton number. So there are several ones. And they tell us that the proton cannot decay because the proton have baryon number +1 and the electron have baryon number 0. So the proton cannot decay into the positron. And that's actually what keeps the proton stable. And of course, if you have some conservation law, that has to come from some underlying symmetry. So that's how we actually explain in the standard model the reason that the proton is stable. There is a baryon number that guarantees that the proton cannot decay. But there's a fundamental difference between baryon number and electric charge. Both of them are conserved charges, right? So if you look at all the things that we do in nature, always we see that the electric charge is conserved, and we also see that baryon number is conserved. The fundamental difference is, from the model building point of view, is that electric charge conservation is something that we impose. It's an input. It's something that no matter to what order we expand our Lagrangian, it should be there. However, lepton number is not something that we impose. It's an accidental symmetry. It's something that arises because we truncated the standard model at dimension 4. If we would go to dimension 6, there will be no baryon number, okay? And another difference is that electric charge comes with a force, the fact that we have the photon that actually does the electromagnetic force, but baryon and lepton number do not come with a force. They're just conservation laws that do not associate themselves with a force. Okay, so that was my very brief introduction to the standard, to high energy physics and the standard model, and that brings me to the first topic of neutrino masses. Unless there's any question, and I'd be happy to discuss any question if anybody has one.
So especially students are encouraged to ask the questions.
Sorry?
So I am just asking students to participate in the questions.
Yeah, please feel free to ask questions, totally free. Okay, so let me move on, and I wanted to discuss the first question, the first open issue, and that's neutrino masses. So what are neutrinos? So kind of give you the shopping list of what are neutrinos. They are neutral fermions, they do not carry electric charge, and they appear massless to a very good approximation. That means that all the neutrinos that we measure so far travel at the speed of light. As you might remember, a few years ago, there was an indication that they travel actually faster than light, but that turned out to be wrong. And everything, as of now, we just see them travel at the speed of light. And we see that they actually come in 3 different flavors. We call them the electron, muon, and tau flavors. And it's not very important what exactly those flavors are. For the sake of our discussion, all I need to know is this flavor, you can think about it as some observable, something that you can measure. And we call it F hat to indicate that this is actually an operator, in quantum mechanics operator. And generally speaking, this thing that we can measure, this observable, have some relation to the mass of the neutrino. When the neutrino is massless, then this new observable flavor commute with the Hamiltonian. That means it's a symmetry of my system. When the mass of the neutrino is not 0, then generally, it's not if and only if, okay? But generally, then my new quantum number flavor doesn't commute with the Hamiltonian, okay? So just this basic fact tell me that if I find that this flavor is not conserved, if I see flavor changing through a process, then I know that it not commute with the Hamiltonian, and then I know that the neutrinos are massive. Okay, I'm not getting into the details of it, but the bottom line is as following. When I say I want to ask, are the neutrino have mass or not, then instead of ask directly the question, can I actually measure the mass of the neutrino, you know, take a little neutrino and put it on the scale, that's something that we cannot do practically. Instead, I use this quantum mechanics thing, and I asking, is flavor commute with the Hamiltonian? Is flavor conserved in a system? If I see that flavor is not conserved in the system, then I know that neutrinos have masses. So how do I actually use it? We're actually looking for places where I can see flavor violation. And the way I do it is I use neutrino oscillation experiment. How do I do neutrino oscillation experiment? I produce, say, a muon neutrino at some point, send it out at the speed of light to far away destination, and far away, I'm looking for tau neutrino. And if I found a tau neutrino far away, I know that flavor is not conserved because I start with something that have flavor mu, and I end up with something that have flavor tau, okay? And actually, there's many different experiments that look for this, you know, from neutrinos coming from the sun. The sun is really far away. Neutrinos that come from cosmic rays, from the upper atmosphere, and then on terrestrial neutrinos, people create neutrinos at CERN and grade them and send them to Gran Sasso, or create them at Fermilab and send them to other places in the US. And when you put it all together, you find that the neutrinos are actually massive, and the mass of the neutrino is few times 10 to the minus 2 electron volt. We don't know the exact number, but we know the rough things, okay? And if you compare it to the mass of the electron, which is 10 to the 6 electron volt, or the mass of the proton is 10 to the 9, you see that this number is very, very small. It's roughly 8 orders of magnitude less than the mass of the electron, which is the lightest fermion that we know, okay, that have masses beside the neutrinos. So the conclusion is that neutrinos are massive, and the masses are extremely tiny, okay? So that's kind of the bottom line of this. So the question is, you know, why they are actually have mass and why they have tiny masses. But the question is actually a little deeper, because I told you that we have this amazing theory that's called the standard model, okay? And then you go to the standard model and test what are the mass of the neutrino in the standard model, and wow, you find that the neutrinos are exactly massless. They are not approximately massless. They are not small. They are exactly massless. And when I say exactly, what do I mean? I mean, oh, there's a symmetry that guarantees it, okay? And the symmetry that guarantees lepton number, this accidental symmetry that I've been talking before. And if you have a symmetry that guarantees that something is massless, then this something is exactly massless in your theory, okay? So in order to account for the experimental fact that neutrino have mass, we know that we have to change the standard model. Okay, we have to add something to the standard model. That's a big statement. The standard model is, as I said, it's a very successful theory. So we had to do something to a very successful theory is a big deal. And there are several ways to do it in order to give neutrino masses. And I want to just talk about one of them, okay? The idea is to add what we call sterile neutrino, sterile heavy fermion. Why we call it sterile? Because it's sterile because it's not charged under any of the forces of the standard model. It's not charged under the strong, weak, or electromagnetic interaction, okay? And the question is, why when I add this extra particle n, why it leads to massive neutrinos, okay? So I was just telling you that I am adding it and it gives massive neutrino, and what I like to explain now is why it's actually doing it. So in order to do it, we are going to go to a little detour into what I call a second look at second-order perturbation theory. And I hope you all remember your undergrad days when you study perturbation theory. And when you study second-order perturbation theory, you say, oh, that's a very cool idea to calculate very small correction to some spectrum, okay? And the idea was that we get a very small correction, say, to the ground state, based on the whole spectrum of the theory. So in first order, I don't care about the rest of the theory. But in second order, somehow I start caring about the whole theory, okay? I sum over all the state of the theory. And now I can actually reverse the logic, okay? So in undergrad physics, we say, I know the spectrum of the theory, and knowing the spectrum of the theory, I can calculate the correction to the ground state. But now I can reverse the order. I said, let's assume that I don't know the spectrum of the theory, but I measure the correction to the ground state. So if I measure the correction to the ground state, I'm indirectly get sensitivity to the high energy states, to the rest of the spectrum, right? So actually looking at second order perturbation theory in this way is kind of nice. It's not that I know the one way to look is that I know the spectrum, I can calculate correction. Another way is that I measure the correction, I get sensitivity, I get probing power into the full theory, okay? So let's take a very simple case, a case of two-level system, where one state have high energy, E1, and the other have small energy, E0. And then I ask, what is the correction to the energy, to the ground state energy? So the correction has to do with the matrix element between the first and with the excited state and the ground state squared over the energy difference. And if I use the fact that E1 is much, much bigger than E0, then I know that the E0, the difference in E0, scale like 1 over the heavy scale, okay? So it's not a very surprising fact. What we're just saying is that when you have second-order perturbation theory, the heavier, the higher the energy of the excited state, the effect on the ground state is smaller, okay? Oops, I have a typo here. Now, all we need to do now when we move from this second-order perturbation theory to particle physics is just to remember that in particle physics, energy become mass, if you like, is E equal mc squared. It's just the fact that all what I was saying here about energy now is actually translate into masses, okay? And I said the mass of the light particle will be proportional to 1 over the mass of the heavy particle, okay? It's basically the same. So how do we get neutrino masses? So actually we have these extra degrees of freedom, and these extra degrees of freedom couples to the light degrees of freedom, and using second order perturbation theory, we get exactly the same thing that we do in normal second order perturbation theory. The mass of the light state, which is the neutrino, which is the light state, is proportional to 1 over the mass of the heavy state. And the proportionality factor is the weak scale, is the mass of the W boson, roughly speaking, okay? And this idea is called the seesaw mechanism. Why seesaw mechanism? So here is a picture of a seesaw. And you see in a seesaw that if I have the heavy guy, the heavier this heavy guy goes down, then the upper this light guy go up. And that's basically a picture way to say that m ni is equal to some number over mn, okay? So I kind of like this cartoon, and I hope that this kind of gives us the very rough explanation of why the neutrino mass are very light. They are very light because the particle that actually is the one that eventually is fundamentally give them the masses is very, very heavy, okay? And then you ask the question, what should be the mass of the heavy particle? and the mass of the heavy particle should be roughly 10 to the 15 GeV, or a little less. You know, it may be 10 to the 10, 10 to the 12 GeV. Much, much, much above the scale of, say, the proton mass, which is 1 GeV, or the weak interaction, which is 100 GeV. Okay? So, let me conclude by asking the question. What is the question about neutrino masses? What is the mechanism that gives neutrino their masses? This is an open question. In particular, is it related to this particle N, this hypothetical particle that I just explained to you how in principle it could lead to neutrino masses? So this is open question number 1 that I wanted to talk about. So before I move to open question number 2, is there any question about are there any questions about open question number 1?
Hello, sir.
Yes.
So my question is not regarding the question number 1, but I want to know, you write perturbation term the delta H. So that's the perturb part in Hamiltonian. So I want to know how you modeled this delta H, like in this particular case, to add the mass in neutrino. Add the mass in simple extended model.
Yes, so the point is that, again, coming back to this second order perturbation theory intuition, then basically what I actually have some coupling, which are something that is above the leading order, that actually connect my light state and my heavy state. So it's connect my neutrino state, the light neutrino state, to the heavy neutrino state, okay? And then you actually have to kind of, if you like, you have to diagonalize a 2x2 matrix, okay? And the 2x2 matrix has to do the leading order mass is 0 for the neutrino, and then you have a very heavy mass for the right-handed neutrino, and then this off-diagonal term, which has to do with is this coupling between the light and the heavy guys, give you this thing at the very end. So it's similar to second-order perturbation theory, but it's not exactly second-order perturbation theory. It's much more like second-order perturbation theory in a two-level system, where you actually have, where your Hamiltonian at the end of the day is a 2x2 matrix.
Okay, sir.
Does it answer the question?
Yes, sir.
Yes, okay, great.
Hi, so I had a question.
Yes.
So you mentioned that the sterile neutrino mass eigenstate is about 10 to the 15 GeV. So how can we conclude that? Or what are the, how do we know that?
Yeah. Yes, so actually, we have this formula here that the mass of the neutrino is roughly the mass of the W squared over the mass of N, okay? And I didn't actually get into what is this sim sign mean, but this sim sign mean that we naively expect that these order 1 numbers here, okay? It's not guaranteed. But assuming that this is order 1, then we know the mass of the W, and we measure the mass of the neutrino to be of order 10 to the minus 2 electron volt. That's how you get this M to Mn, okay? So this is 10 to the minus 2 electron volt. The mass of the W is 10 to the 11 electron volt. So 10 to the 11 electron volt, that's what gives you the 10 to the 15 GeV, okay? So it's
Okay,
basically
thanks.
using this formula, okay?
Okay, thank you.
Good. Okay, so can I move on? And let me move to the second question. So I want to talk matter, antimatter, and CP violation. So we all know antimatter exists. You know, we've seen the positrons. Positrons become actually part of almost everyday life. You know, we use it in medical equipment and everything like this. And we know that the positron, which is the antimatter of the electron, is the exact mirror image of the electron. We just say, you know, they have exactly the same mass, exactly the same spin, exactly the same G factor. The only difference is that the electric charge become positive rather than negative, and actually more generally, all the quantum number become opposite. And the formal transformation between matter and antimatter, it's what we call CP, charge conjugation time parity, okay? And we also know that matter and antimatter cannot really coexist. When we take an electron and a positron, they annihilate into gamma rays, basically. And they just become pure energy. And then we also know that the universe has a net positive baryon number. That is that actually in the universe, there's more baryons than antibaryons. There's more protons than antiproton and more neutrons than antineutrons, okay? And that's actually a little bit confusing because in the standard model, baryon number is an accidental symmetry. That's actually guaranteed that we have the same number of matter and antimatter particle, basically 0. And if you remember when we talk about the neutrino, the surprising fact that we had an accidental symmetry, which is lepton number, that seems to be broken when I require neutrino masses. And here I say this accidental symmetry of baryon number guarantee that we have no baryon number in the universe. But actually, when you look around you, all you see is baryons. And you can actually do it. Just look around you, and everything you see is baryon. Okay, when you look into your screen, it's actually baryons. You just see baryon. You don't see antibaryons around you. Okay? And we can actually measure it, measure the total number of baryons in the universe. And we usually like to normalize it to the number of CMB photons that we have. And we get this parameter. It's called the eta parameter. And this eta parameter is a very small number. It's of order 10 to the minus 10. Okay? So what I was just telling you in this transparency, I just throw a lot of information on you. And I was just telling you that there are matter and antimatter exist. In the standard model, they are totally treated the same. And we measure it, and it exists to 10 to the minus 10. So that actually gives us two questions. The first question is, why at all this number is not zero? Why we actually have more matter than antimatter around us if they are mirror images? If they are exactly the same, they should be treated exactly the same, and we should get the same number. And moreover, even if we understand like why we have more matter than antimatter around us, can we explain this measure value? Can we explain eta? So this is like the first order question, why it's not zero. And once we understand this, we have to ask, can we actually explain this number 10 to the minus 10? So there's several kind of ideas how you get this idea of baryogenesis. So baryogenesis is a general name of the system that create baryons for us. And the ways are the following. You know, one can say, you know, the universe was just created that there was no, that, you know, with net baryon numbers. Or maybe there's some separation. Maybe actually here's this baryon and the antibaryon just sits somewhere far out. These two explanations, I'm not going to get into details, are ruled out by now. And that leaves us with the third explanation. The third explanation is that baryons are produced actually dynamically at the early universe. So sometimes in the Big Bang, in the very early stages of the universe started in a symmetric combination of matter and antimatter, same number of baryons and antibaryons. And somehow during the evolution of the universe, there was some mechanism that actually result in more baryons than antibaryons. Okay? And we really like the third possibilities because it seems to actually working, and we can actually do some calculation. And the first person who asked those questions was Andrei Sakharov. It's an amazing story about him. You know, the guy was in the USSR, fight for human rights, put in Siberia, and still did some of the most amazing physics ever done. One thing is baryogenesis, you know, what I'm going to tell you right now. And the other one that is also very well known is just the fact that he was the first person who actually suggests that in the CMB we should see the acoustic oscillation. Okay? The only thing that he missed, he said, we will never be able to see those acoustic oscillations. And of course, now we all saw those acoustic oscillations in the CMB. But he was the first person who understood that we should see them. Anyway, so coming back to our story about Sakharov, Sakharov came with those three conditions, okay? He said, in order to dynamically generate baryon number, we need to have the following three conditions. We must have some underlying process that violates baryon number. So if baryon number is exact symmetry, we can never actually get it. So let's assume there's some particle X that could decay into a proton and an electron, okay? It's violate baryon number, assuming X do not carry baryon number, okay? So I can generate some protons. The second condition that I need C and CP violation in order for the process X go to P plus would be different from the anti-process, which is X bar go to P minus. So if matter and antimatter are exact mirror image of each other, then the probability of creating proton from X is the same as the probability of creating antiproton from X bar. However, if we have CP violation, which means that matter and antimatter are not exactly mirror image of each other, then I should see that I create more proton than antiproton. And the third one, I need deviation from equilibrium. Why? Because if I have equilibrium, then I can create proton, but then I have also the inverse process that the protons can annihilate back into X. So I need deviation from equilibrium such that the process that creates protons will be more effective than the process that destroys protons. And it's kind of interesting that it's basically if and only if. If you want to have a baryogenesis, if you want to understand the mechanism that end up in a universe with matter, those three conditions must be satisfied. So then you ask, do we have actually those conditions in the standard model? And amazingly, they are satisfied in the standard model in a very complicated and much non-trivial ways. So I actually want to very quickly explain to you how it is actually done in the standard model. So we actually do have baryon number violation processes, something called ailerons. So I was just telling you that baryon number is an accidental symmetry of the standard model. And that's really the thing that makes sure that the proton is stable, etc., etc. So what are those ailerons? So those ailerons are some non-perturbative effects that in some way you can think about them as tunneling processes. So they will never appear in perturbation theory because they are tunneling processes. And they actually result in some baryon number violation. And moreover, these processes are very temperature dependent. At zero temperature, they are highly suppressed. They are exponentially suppressed, and they're basically zero. It's go like e to the minus 500, roughly, which is also known as zero, right? However, at high temperatures, they are very effective. And actually, if you go to temperature above the electroweak phase transition, which when you go to temperature above 100 GeV, which is much above anything that we see in nature, it's much above the center of the sun, it's much above what we see in supernova, it's much above anything, then those processes are actually they are very effective. So, we know about them theoretically. So in the early universe, in the Big Bang, the temperature presumably were much above 100 GeV, they were actually very effective. We know that the weak interaction actually violates C and CP. I'm not going to get into much of the details, but that's actually where most of my research is about this statement. And then I'm going to tell you how we actually have deviation from thermal equilibrium. The deviation from thermal equilibrium have to do with the way we have the electroweak phase transition. So what's happening is that in the very early universe, we didn't have a symmetry breaking in the standard model. So the weak interaction, the masses of the W and Z were still zero, and the weak interaction was long range, like the electromagnetism. And then we have a phase transition where the W and the Z acquires mass. And what happened in a phase transition? So when you have a first order phase transition, what you have is basically like where you have when you boil water. You have a little bubble, and this bubble grows. Like when you boil water, it starts to grow, but at the same time, it actually go up of the water and disappear out of the water. But if you don't have gravity, then what would have happened is that the waters, they will just have the little bubble in the water, and it starts growing. What is not in equilibrium in this process? What is not in equilibrium is the growth of the bubble. Okay, the wall of the bubble is out of equilibrium because it only goes one direction. It actually goes from the what we call the real vacuum from the forced vacuum into the real vacuum, or the other way around, from the real vacuum into the forced vacuum. Okay, so we actually get out of equilibrium things. Okay, so actually the standard model, within the standard model, in a very complicated way, we can generate a world with matter. That's a very nice statement. So then you ask the question, okay, how much matter do we get? And you find out that you are almost there. Okay, you do the calculation, and you find out that in the standard model, the amount of matter over antimatter that you have is about 10 to the minus 25 compared to 10 to the minus 10. Okay, and I hope you feel how much it's like a miss. Okay, you miss by a mere 15 order of magnitudes. Okay, I know it sounds like, hey, 15 order is a lot, but actually it's not too much. You have to go through a lot of things in order to actually get away from zero. That's the big deal. So you finally get away from zero, and then you just miss by numerical factor. Okay, so the open question is as following: what is the source of baryons in the universe? We know it cannot be the standard model, despite the fact that the standard model actually does give us something, but it doesn't give us the right amount. So there's actually many ways to explain those things. Okay, there's many proposals. We don't know which was the right one. And I want to actually tell you about one of them, which is called leptogenesis. So you remember this N field that I was introduced talking about the first question about neutrino masses? we can actually generate lepton number versus this n decay. When this heavy particle n is produced in the early universe, and it's decay. And then when it's decay at very high temperature, it creates some lepton asymmetry. And this lepton asymmetry is converted into baryon asymmetry through these phalerons. I know it sounds a little like I'm throwing some information to you, but the bottom line is as following, that actually this particle n that I was postulating exists in order to explain neutrino masses actually could give us a universe with baryons, okay, as long as the mass of this n is roughly bigger than about 10 to the 11 GeV, okay? So that brings me to question number 2. What is the mechanism that generates baryons in the universe? In particular, is it related to n, to this particle n? So that's done with question number 2. And if anybody has question about question number 2, I will love to try to answer them. Except, of course, that I don't know the answer to the question itself.
Hello, sir. Hello. Am I audible?
Sir, I have a question.
Sure.
Why the second Sakharov condition why C and CP should violate simultaneously?
Oh, so basically, if you have C or CP conservation, then this relation is guaranteed. So if x go to p plus e minus, the same as x bar going to p minus f, is guaranteed when you have C and CP. If you have either C or CP. Now,
Yes.
the condition for C is not very important because by now we know that C is like totally breaks everywhere, okay? Just when you're just talking about the fermion as two components fermion, automatically C is violated. But think about, if you think about a theory where everything is 4-component fermions, okay? Then C is actually and you can actually impose C and have CP violation. So it's a little bit hard to think about C violation and CP conserving, because like the way we build models right now, CP is much more fun. It's much harder to break than C, but you can actually build model where C is conserving and CP is not, and that will be enough to guarantee this condition. Okay, for massive Dirac fermions, it's very important. It's massive Dirac fermion. So you think about a Dirac theory. I know I cannot really get into the details, so I will just give you kind of the right answer. The full details, you just have to work out the algebra.
Okay, thank you.
Any more questions?
Yeah, sorry. So I have one question.
Sure.
Since this capital N that you're talking about, it is the source of the baryon number, etc., is producing that. But my question is that how did it come in the very first place? I mean, from where you're getting this N?
Okay, so this has become a detailed question about the model, and there are several ways to create this N. The simpler one is that this N is just is in thermal equilibrium at the very early universe. So this N should have some coupling to some other fields, and when you actually after inflation, so the way we think about the usual Big Bang picture is we have some inflation, and after inflation ends in the process that's called reheat, and after reheat we have a universe that is in thermal equilibrium, and then all the standard model degrees of freedom are in thermal equilibrium. So we can actually have a model where this N has enough coupling with some other particle that has become part of in thermal equilibrium. Okay, so that's one mechanism. There's actually several other mechanisms to guarantee that you can actually have enough of those N. The simpler one, as I said, is that this N is in thermal equilibrium, and this condition that the Mn is larger than 10 to the 11 GeV actually has to do with the assumption that it's in thermal equilibrium. But you can actually avoid this, and you can have Mn at lower energy if you have some other ways to create it.
Okay. Thank you, sir.
Okay.
Yes.
Hello. Am I audible?
Okay, so let me move on to the third question. That's the question of why the absolute value of the electron and the proton is the same charge. So, we can just say, just an accident. It just happened to be that all the particles in nature have charges which are like 0, third, 2/3, 1 of the mass of the charge of the electron. But history tells us that when you see some structure, there's some underlying explanation. And I think Dirac was the first person who came with some cool idea that he said, if there exists some magnetic monopoles, we understand it. It might be the right answer, but I want to talk about a third possibility, And the third possibility is if the U1 electromagnetism is the symmetry that we impose on electromagnetism is actually part of a rotation in a larger space. So I want to actually very quickly explain to you why this actually gives us charge quantization, why that actually tell us that the charges of all particle in nature should be a product of some fundamental charge. So what is charge? Okay, so charge, that's a kind of a, this transfer is a little bit abstract. So if you never seen it, you might get lost a little bit, but hopefully not. So how do I define charge? So let's say I have some field or some wave function, and I rotate this wave function by some arbitrary angle theta, okay? And I assign for each of my particle, I assign another real number q, okay? And I say my electron carry and the number q is -1. For the proton, this number q is +1. For the quark, the number q is -1/3 or 2/3, etc. Okay? And I perform this rotation by an angle theta to all of my fields in my Lagrangian. Okay? Now think about rotation in 2 and 3 dimensions. What happens in 2 dimensions? In 2 dimensions, let's say I take some vector r, and I rotate this vector r by some theta. This q can be any number. It's just rotation in a plane. However, what happens when I move to 3 dimensions? Then something miracle happens. This q cannot be anything. This cube actually is a matrix, okay? And this matrix cannot be anything. It must satisfy the famous commutation relation of the SU2 algebra, okay? This is fundamentally related to the fact that 2-dimensional rotation are commutative. I mean, it doesn't matter the order that you do them, but in 3 dimensions, when you commute things in 3 dimensions, actually things are quantized, okay? There's something not commutative, and these things actually cannot be anything, okay? And you know it from quantum mechanics, that the quantum number of angular momentum is only 0, half, etc., where quantum number for momentum can be anything, because momentum is basically just rotation on 1 dimension, okay? Now, think about the following thing. Let's say that you have a rotation in 3 dimensions, but for some reason you break the rotation in 1 dimension, and you stay in rotation in a plane. Think about a hydrogen atom when you put in magnetic field. Then you start with the rotation in 3 dimensions, and once you put the magnetic field, you have only rotation in the XY plane, because the magnetic field is always in the Z direction. You never put the magnetic field in any other direction, right? So you have a magnetic field in the Z direction, and then you have only symmetry in the 2 dimension. So if you don't know that you actually start from a 3-dimension rotation, and you look and you say, like, why the splitting is like, why we have some kind of quantization in rotation in the 2 dimension? And the answer is because it's fundamentally 3 dimension. So that's the bottom line. Non-abelian symmetries imply charge quantization. Okay, so rotation in 2 dimension, when it's part of a 3 dimension, give me quantization of this quantum number. So even if you didn't really follow the full thing, then I was very quick on here. All I want to say is this following. If I have rotation in a plane that is actually fundamentally part of a rotation in a higher thing, I get charge quantization. How this is related to the standard model and particle physics? Maybe we have what we call grand unified theory. GUT stands for grand unified theory. That actually our theory is part of a bigger theory, okay? It's part of the grand unified theory. And in this case, all the standard model fields are part of a bigger multiplate, okay? They are not like the electron and the neutrino is a doublet under SU2. Here, the things are part of a bigger multiplate, and then eventually it's break into the standard model one. And then it implies actually that the electron and the proton must have the same charge. Okay, so I want to emphasize what's going on here. In the standard model, when I build the standard model, it was an input. I decided, when I built the model, I decided to give the electron and the proton the same charge. When I put the standard model into a more fundamental theory, okay, then the fact that the electron and the proton have the same charge is an output. And that's a big deal. It's not an input, it's an output. That is a result of something more fundamental. And it's basically a result of the fact that the full theory, it's the full fundamental symmetry is non-abelian. So how does it work? We take the standard model, we put them into some bigger group, SU5, for example, take it SO10, and then this SO10 is rotation in 10-dimensional real space eventually break down to the standard model group. Okay? And in the standard model, we have 15 degrees of freedom. And in SO10, we have 16. So actually, it works almost exactly, because I take all my particles of the standard model and put them into this bigger representation. And I found that I have actually 1 extra degrees of freedom. So that might be a source of worry, because I know that that really works. But then you look and say, what is this extra degrees of freedom? And you find that this extra degrees of freedom is exactly the same property of our friend, this n, that we already talked about in the previous 2 questions. Okay? And actually, when you work out the details, you find that the mass of this n in this theory is close to the gut breaking scale. Okay? It's the scale where this breaking actually happened. Okay? And now the question, what is the scale that this has happened? So we actually have some indication, and this indication has to do with the way that the coupling actually unify. And I'm not going into the details of grand unified theories. All I'm just telling you is that when you look at the strong, the weak, and the electromagnetic interaction of the standard model, and you ask what's happened to them when you actually go to high energy, you find that roughly at 10 to the 16 GeV, they all become 1. And that's kind of the indication that you actually have grand unified theory. That at this point, we have the breaking of this 1 theory into the 3 forces that we know today. So we know that grand unified theory tell me that the thing is about 10 to the 16, and they tell me that the mass of this 1 extra degrees of freedom that I may have been worried about a little bit is actually roughly of order 10 to the 16, maybe a little less. There's some factors of order 1 that enter there. Okay? So let's bring me to the 3rd question, and the 3rd question is grand unified theory realized in nature? And in particular, is this specific grand unified theory that I was telling you about is the one that realized, and we have this extra particle, it predict this extra particle n. So that's my 3rd question, and I'd be happy to answer any question about the 3rd question.
Hello, can you hear me?
Yes. Yeah, definitely. That's great.
I have one question. So, in grand unified theories, these baryons and leptons are naturally becomes the part of the same multiplet.
Exactly.
So we naturally have baryon number violation.
Exactly.
So why do we need this n to be present in the grand unified theory?
Okay, so
I mean, the question is why this extra? Why the extra degrees of to be? Okay.
So the point is that we can actually have baryogenesis, for example, and we can have neutrino masses also in some other mechanisms through grand unified theory. The point is actually, and that's kind of an interesting thing, is that actually when you work out the details, you find that most of these fundamental grand unified theory violation things, they correspond to particles that we call the X and Y particle, like deep names, like how come people come with these names, right? So they are called the X and Y particle, and those X and Y particles could generate baryogenesis for you, okay? When you work out the details, you find that many of those models actually are ruled out. They are not actually, the specific parameters that are required actually give you a problem. And in particular, it has to do with the fact that actually, I'm not going to get into much detail that you have the difference between the B plus L and B minus L, that, you know, these ferrons are conserved B minus L and not B plus L, etc. Okay? So you actually have to work out a little more to actually get baryogenesis in grand unified without the N. But my real answer is as following. I mean, you just take the theory, you just say, I really like SO10, I write the SO10, I have this N. And when you work out the details, it turns out that actually this N gives you baryogenesis, and also there's some other contribution to baryogenesis. There's not like one contribution. And it turns out that actually the contribution from the N is actually the dominant one. Okay, so that's the real answer. The real answer is just yes, you have to take into account all contributions, and it depends on the model parameters. And in big chunks of the model parameters, the most important contribution come from the N particle.
Yeah, thanks. Got it.
Hello, I have a question.
Sure.
In the previous slide, you showed the diagram, the accelerators, the present accelerators energy scale you have shown, yes. So how one can attain this gut energy scale of 10 power 16 at the experiments?
Oh, so there's no way we can get there, okay? So the hope, how do we hope to actually prove this theory? So we hope to prove this theory basically in the same sense that I was telling you about this new look of second order perturbation theory. You want to look about some short distance effect of it. And the most amazing short distance effect of this theory is that in most of them, the proton should decay. So what we are doing, we actually look for proton decay. And I really hope that soon we're going to see the proton decay. That would be really amazing. And that would be a very clear indication that we have something going on here. Okay? There's a few other ways to look for it. And the other way is actually what I'm telling you today. Looking for neutrino masses and baryogenesis actually indirectly also tell you something about what's going on here. Okay? And we also hope to see something in cosmology. But this is not so easy. So it's not easy to actually probe grand unified theory. But I would say that if we actually see like proton decay, and if we see some things in neutrino physics, in particular if we see neutrinoless double beta decay, that will be a strong indication that this is correct. But we cannot really probe it because the energy are just too high. Okay, so let me move to the very end of my talk, now that we actually have 3 questions. And we already saw that those 3 questions kind of all related to this particle n. And we put it all together. Why neutrinos are massive? Why they end up with universe with matter? Do we have grand unified theory? And I was telling you that all kind of tell you that maybe we have some new particle that we'll call this n. So now the question is, can the same n, the same one particle n with a given property can give you all those 3 things? So what is the answer? The answer is yes. And you can tell that this is actually very important. How do you know that this is very important? Because I use very big font. And when you use a very big font, you use a very big font because you want to say something is very important. Okay? So I hope I made my point here. Okay? What I really want to say is that it's not enough that we have this one particle that explains 3 different things. A particle. It's the same particle. So we have one particle with the same property, the same mass, the same coupling, the same everything. It's the same particle that actually do everything. So when you have one theory and you find that this particle actually indicates that you have grand unified theory, it's actually the source of the reason that we have baryon number in the universe. It's also really the fundamental reason that neutrinos have very, very small masses. Okay? So I hope I made my point. It is basically all I wanted to get out of this colloquium, for you to remember this. There's one particle that explains all 3 open questions. It doesn't mean that that's the right answer, but it means that it could be the right answer. So what next? So I'm not going to get into many details because I have like 1 minute left. And what I want to say is that there's many more experiment runnings and there are many that plan that actually look for all those kind of things. We look for neutrino oscillation. We look for CP violation in neutrino oscillation. Very interesting. We keep looking for proton decay, and I really hope that we're going to see it. We look for neutrinos double beta decay. There's actually more. And the hope is that in 10 years from now, we're just going to have much more information from low energy that we'll be able to actually probe and put much more constraint on the high energy model, and it will just emerge that basically the only model that seems reasonable is the one that actually have this n that will be a big triumph for this kind of theory. So let me conclude, and let me just say that maybe thanks to the neutrino we are all here, that we have baryons, we understand grand unified, and we do physics. So that's it. Thank you very much. Question.
Hi, sir. I have a question.
Wow. Yes, go ahead.
Yeah, I have a question. Can you hear me, sir?
Yeah. I definitely can hear you.
You can go ahead.
So my question is that, yes. So my question is, as you have said that the baryon number of conservation is an accidental symmetry within the standard model, that is, if it follows the gauge group SU3C cross SU12 cross U1Y. So can it happen that the baryon number can actually violate in SO10 models? And if that happens, so can this lead to a natural explanation of CPV that we see
So, so the fact that in SO10 we have baryon number violation, that's just from the construction of SO10, the answer is right. We have a baryon number violation, and when you actually take your SO10 and write it and match it into the standard model, that appears as a higher dimension operator in the standard model. That's the thing that we actually truncated. So you actually take SO10, write the SO10 as an expansion of the standard model, and you find that the baryon number violation appears as a dimension 6 operator in the standard model. Now about CP violation, then this is actually not totally related. The fact that we have CP violation in the standard model is totally explained within the standard model, okay? What we actually, this CP violation that we have in the standard model that explain everything we see in basically in chaos charm and beauty decay, so we explain everything we see in meson physics, does not explain the baryon asymmetry of the universe, okay? But and it's not the only thing that we cannot explain. So in order to explain within the standard model to explain the baryon asymmetry of the universe, we have two things that doesn't work. It's the fact that CP violation is not large enough, and the fact that the wave phase transition is not strong enough. The deviation from thermal equilibrium is not strong enough. So the point is that within SO10, if this mechanism that I was telling you is correct, there must be extra sources of CP violation that do not affect us in what we see so far in the lab, but will affect us in some other places, for example, in the baryon asymmetry of the universe, and maybe in other places like electric dipole moment of the neutron, which is another direction that people are actually looking for extra sources of CP violation.
Thank you, sir. So this means that, sir, even if we move to higher dimensions, so we need to actually look for other sources of CP violation such that it can explain that matter-antimatter asymmetry. That's
exactly.
That's the, yeah, okay.
Exactly. So basically, you have to move to dimension 6 in the standard model, and in this dimension 6, it gives you both a baryon number violation and it gives you extra sources of CP violation. Okay, now people actually been playing with the idea that this dimension 6 give you only baryon number violation and the CP violation come from the dimension 4, but you can work it out, but there's no reason to do it. Once you have dimension 6, then naturally you have both, and that's kind of what might be the right answer. But of course, it's still, we are very much in the dark. What is the exact mechanism?
Thanks a lot, sir. Thanks.
Sure.
So Yuval, let me take one question from Facebook, because we are also streaming live on Facebook. And so one student is asking, is the preponderance of matter due to violation of Lorentz symmetry at some point in the course of the evolution of the universe?
So you talk about Lorentz symmetry and Lorentz symmetry violation, but
is the preponderance of matter due to violation of Lorentz symmetry at some point in the course of evolution of the universe?
So as far as we know, Lorentz symmetry is exact. Okay, and actually everything that we built, all the model that we built, Lorentz symmetry is exact. Okay, of course, when you have matter, then you have an effective Lorentz violation. Of course, when I sit here, Lorentz, if I treat, my background as an effective background, then I have an effective Lorentz violation. But fundamentally, we believe that Lorentz symmetry is actually exact. Okay? Now, people had been trying to build models where Lorentz violation is fundamentally broken. And yes, some model exists, but they actually have a lot of problems. It creates a lot of inconsistent with experiment, and none of these models seems very attractive to me. But it's a personal story. What I want to say is that actually, in order to explain the baryon asymmetry of the universe, we do not need any Lorentz invariant violation. I hope it answered the question.
Yeah. So, any other question from audience?
So,
hello, am I audible?
Yeah.
Yes.
Shall I ask?
Yeah, you can go ahead.
Yeah. So you said that the scale of this n is very high.
Yes.
So it should be very high to explain those baryon symmetry, neutrino mass, and all these things. So at the current scenario, our experimental limit to do the theory experimentally feasible is around TeV scale.
That's right.
what should motivate us to go and study at this scale? And because whenever we do a model, anyone can do some study at different scale. But one should ensure that we should get some experimental evidence or something like that. How can we prove this if something goes right?
I totally understand this question. Of course, that's a very, very, very important question that we all, have to discuss it and answer. And the point is as following. So what I was telling you, the story today, is of course part of the big picture of high energy physics, right? And if my story is correct, then basically there's nothing we're going to see nothing at the TeV scale. So basically what I'm telling you, that if we try to answer those little questions that those very important questions that I was discussing today, this question has nothing to do with the TeV scale, okay? So if you say, all I care about is those three questions that Yuval was actually saying today, we don't care about DLHC. And I was telling you what kind of probes we are actually going. We're going through proton decay, neutrinoless double beta decay, electric dipole moment. All of those experiments, I explained that at very low energy, okay? So actually, in some way, this kind of the seesaw idea, we have to probe things at very low energy in order to actually get very, very small deviation of low energy to get something at the very high energy. So why do we have DLHC? And if you notice, I didn't mention DLHC the whole time in this talk, although this is our biggest machine. The answer is that there's actually other open question in physics. And those other open questions in physics are those that actually tell us that we are very excited to see something new at DLHC. And these are basically related to something called the hierarchy problem. And I totally didn't touch it at all. And basically, it's actually come to some deeper question than what I was talking about today. So what I was talking about today, I say, I told you all those stories, and say, well, it's kind of hint to the fact that we have some N particle that is much heavier than the particles that we have. And then you can ask the following question, let's assume that this particle exists. Why this particle is so much heavier than the particles that we see? Why this N is at the 10 to the 15 GeV, where our particles, the weak interaction is at 10 to the 2 GeV? And the answer is we don't know. And this is a very, very important question that's in some way related to this question that we call the hierarchy problem. So yes, the reason that we have DLHC is to solve many other problems and somehow even deeper question that I was asking today. Hope it answered the question.
Let's hope for the best for the future.
Yes, of course.
Definitely. Yes. Thank you.
I have one question regarding this question number 2. So you mentioned that the universe can be created in such a way that the baryons are at one side of the universe and antibaryons are at the other side of the universe. So you were basically talking about this electroweak baryogenesis, right?
No. So what I was just saying that very, very generically, you say, how do we really know that the total baryon number is 0? All we know that in our patch of the universe, we have some positive. Maybe there's some other patch over the horizon where actually the baryon number is exactly opposite, such that the total baryon of the two universes are 0. So actually baryon number is 0. And there's some mechanism that actually separate them. Okay? Yeah. And basically it doesn't work for many reasons. The simpler reason it doesn't work just because of entropy. I mean, the universe, you like to increase entropy, not to decrease it. So separation actually decreases entropy. Basically, thermodynamics tell you that whatever mechanism happened in the Big Bang, it actually like to create you cannot, there's no reason for them to be separately in space. But, I mean, there's some other reason that tells you that actually any calculation tells you that, you come to equilibrium. And equilibrium cannot have two things separated. Okay. All I wanted to say is this idea ruled out.
Yeah. Ruled out from theoretical arguments, right? Not by any...
Yes. Yeah. I mean, it's ruled out experimentally within the horizon. So within the horizon, we know there's no patches of antimatter, basically because if there was patches of antimatter within the horizon, we will see the annihilation in the border between these patches. Yeah. And we don't see those gamma rays. But if it's beyond the horizon, then it becomes almost philosophical, because by definition, not by definition, but just by our basic understanding of horizons, we will not be able to see beyond the horizon, right? So we cannot see it. But theoretically, we say even we cannot create it even beyond the horizon theoretically.
Yeah, thanks.
So Yuval, would you like to take more questions, or should we?
Sure, I'm happy if there are more questions.
Okay, students, please.
Okay.
Yeah, so I
had a question.
Yeah, Lopamudra, go ahead.
Are there any cosmological observations through which we can, look for sterile neutrinos?
So the story of sterile neutrinos is extremely complicated, and it's very hard to actually see them. And what we are talking about, so here is a little bit of a language issue. So we have heavy sterile neutrinos and light sterile neutrinos. So this N particle that I was telling you, it could actually be very light. It could be as light as our standard model neutrinos. And when it's this light, we call them sterile neutrinos. Okay, and we can actually see them in cosmology. But these sterile neutrinos, these light sterile neutrinos, are not directly related to the heavy sterile neutrino that I was talking about. So it's a matter of language. Okay, we call both sterile neutrinos, but we mean the different things. So the answer is yes. If we actually have sterile neutrinos, we can see them. We can see them in places like Big Bang nuclear synthesis. We can actually see them in the CMB. We can see signal in the CMB of those sterile neutrinos. But they are the light ones and not the heavy ones.
Okay, thanks.
Okay, so I had a question. You talked about the mass of the sterile neutrino, which is required to explain all the three. But could you also tell us about the coupling, the order of magnitude of the coupling?
Yes. So when I talk about, I talk about this N in three different categories. So when I talk about the N in just looking for the first question, that's the neutrino masses. Then actually what I really know, I don't know the mass. What I know the product of coupling squared over the mass. That's what I know.
Yes.
So the lightest the sterile neutrino is, the coupling have to be smaller. Okay? And actually you can think about making the sterile neutrino as light as the electron mass, but then the coupling are so tiny that basically we'll never be able to produce it because the coupling is so small. So that's why it's so hard to deal with it. Either it's too heavy, so we cannot produce it, or when it's light, then the coupling is very small. When I talk about the other two questions, then actually we know that the coupling cannot be small. So when we talk about the baryogenesis, we know that the coupling has to be somewhat large, okay? And that gives us this bound of 10 to the 11 thing, and the coupling has to be of order, 10 to the minus 2 or above. And when we talk about the third question, the grand unified theory, we know actually that the coupling is roughly the same as the Yukawa couplings that we have in the standard model. So at the end of the day, in each of those three questions, we have some different bounds on the combination of coupling and mass. And when you put it all together, I had a plot that I took it out just, for the sake of time, knowing that I will not have time to show it. There's actually a plot where people actually took those three different questions together and plot it, and you find that actually the coupling are going between something like 10 to the 1 and 10 to the minus 2, and they must go between 10 to the minus 11 and 10 to the 15. 10 to the 11 and 10 to the 15 G.
Okay. Thank you.
Sure.
Okay, sir. Am I audible, sir?
Yes, I do hear you.
Yeah. So I was okay. While giving, while you were saying about this out of the equilibrium decay, you said that the growth of the bubble was out of equilibrium at that time.
Yes.
Would you please elaborate how they were out of equilibrium? In a shorter way, or?
Yeah. So basically, think about the fact that this out of equilibrium actually create a time direction. Okay. So very, very naively think about when you are in equilibrium, you have T go to minus T symmetry, right? That's the meaning of equilibrium. Yes? So any time that you have an error of time, when you can actually tell the times go on, you're out of equilibrium. Think about it in thermodynamics sense. When you're in equilibrium, your entropy doesn't change, right? So when you're out of equilibrium, only then entropy can grow. That's the second law of thermodynamics. Make sense? So anything, basically, in any process that you can tell, I can tell you that something go forward, you know you're out of equilibrium, basically. And that's what happens when you have a bubble grows. So when you actually have the phase transition, what's happened is that the temperature goes down, okay? And locally, you have out of equilibrium because the bubble actually just go in one direction. And what's happened at the bubble wall, again, think about water. What's happened in the bubble was that inside the bubble, your water are in gas phase, and outside they are liquid, okay? And then what's happened when you cross? What's happened when you cross, okay? So when you cross, the bubble kind of grow into the liquid, and what's happened is that the bubble actually pick a drop of liquid water, and then immediately this liquid water kind of become gas. Okay, that's what's happened at the border. Yes, and it's out of equilibrium in the sense that at the border there's only one direction. There's only liquid become gas. You don't have the gas become liquid, and that's what happens when you are in equilibrium.
And how will we correlate with our case? I mean, for our case, particle will get mass.
Exactly. What's happening in our case is as following. Inside the bubble, the particles are massive, and outside the bubble, the particles are massless. Okay?
Okay.
So what's happening is that basically the bubbles kind of go, and it's meet a massless particle and make it into massive particle as it's keep kind of going into when the bubble grows. Okay?
Okay.
And in this process, you actually have CP violation. And the reason is that in the standard model, the mechanism that gives masses to the fermion has to do through the Yukawa coupling, and the Yukawa coupling is actually exactly where the phase of the CKM metric, the phase of CP violation actually enters. So you kind of think that when the bubble actually kind of hit you from the massless part into the massive part, it has to go through the
CP violation.
Yes. Yeah. But again, I mean, the whole story of the bubble it's a very elaborate process, and there's like so much that we need to discuss. So I can give you this really nice hand wave argument, but at the end of the day, you just have to kind of really do the algebra. But I hope that you understand like why there is a out of equilibrium and why eventually it's actually had to do with CP violation, so we can actually get more baryon than anti-baryon inside the well.
Yes, sir. Thank you, sir.
So we have time for one last question.
Hello. Sir, may I go?
Yes, please go ahead.
Hello, may I go, sir?
Yes.
Okay. You are very much excited about the proton decay for the GUT, and so my question is up to what precision we should go for the measurement, and currently which experiment is on this issue working?
Yes, so the question is how far we should push in proton decay. So the answer is, of course, we should keep pushing. And the point is as following, is that the sensitivity is, you change by a little bit the mass of these heavy guys, and the rate of proton decay scale like the mass of the heavy guy to the fourth power, okay? So just changing the mass of the heavy guy by a factor of 2 result in factor of 16 in the rate of proton decay. Now the situation is actually more complicated, because actually when you calculate where is this scale, the sensitivity of the scale to the measurement of, how we predict this 10 to the 16 that I was telling you, you have actually an exponential sensitivity. Okay, so if we actually were off by a little bit by the measurement of the strong coupling constant, that have an exponential sensitivity on the magnitude of this number, and then it's already getting the fourth power. So if we change, say, the magnitude of the strong coupling by 1 per mil, it's going to change the rate from proton decay by a factor of 100. Okay, so unfortunately, like, we are exactly where it should be, but with this exponential sensitivity, we don't know. So we have a rough prediction, but in physics we think logarithmic scale, and experimental is done in linear scale. So that's really the problem. So I don't know how far we should go, but the point is that we are where we could hope to find it, but it's like a 50-50 chance.
So,
okay, thank you, sir.
Sure.
Okay, so see that the things can keep on going, and but every good thing has to end at some point. And this is old saying also that you can gauge the quality of talk from the post-talk questions, and you can see that the kind of questions and how many questions are coming from students. So it's really great to have you here, Yuval, and Tuda Rabba for all these things. And,
amazing, you remember all your Hebrew. That's great to hear.
You salutation. So, Somitro.
Thank you very much, everybody.
Somitro, just unmute your mic. Please say something.
Thanks, Yuval, for all your support.
Great. I'm very happy.
Great.
I'm happy to see so many people and get so many interesting questions. And great to see so many of my old friends around. Raul and Sorov and Anjad. I didn't talk too much to Anjad. Maybe there were others, and Sumitra. Maybe others that I missed.
Suvendu is there.
Nita is also there.
Suvendu is also there.
Maybe. Okay. Hi.
Nita is also there.
Nita, hi.
Yeah.
Anyway, so hopefully, as I said,
we should get you
to come. Hopefully, at some point, I'll be able to really come. It's been so long since I've been to India.
Really love it.
I love it.
Yes.
So I love to come and visit again at some point.
Yes, we'd love to have
Hopefully
you.
We'll be back.
Yeah.
Thank you. Okay.
Thank you.
Have a good night.
Okay.
Yeah,
Bye.
thank you.
Bye.
Bye, Yuval.